Hey y'all, it's your main math teacher, Mr. Boyden. I'm back at it again today, and I've been thinking about something. In geometry, we always talk about angles and sides and vertices and lately apophthegms, and it's come to my attention that because of that, we have not been very well rounded. And you know what? That's going to change today because today we're going to start talking about circles. So in order to do that, let's start by understanding what a circle is. People know that circles are round, of course, and we think, okay, the circle's the whole thing, or we say a pizza is a circle. A pizza's a lot more than a circle, actually. Why is that? Because, well, all a circle is, it's just a collection of infinitely many points that are equidistant to some other point, and we call that point the center. So the center is here. The circle is all this stuff out here in pink. This thing going across the middle here, that is not part of the circle. It's a measurement of the circle, but it's not part of the circle. And this right here, that's not part of the circle either. That's a measurement of the circle. This point, is that part of the circle? No. It's the collection of the points that are an equal distance from that point in the center. And then let's fill in this blank. The distance from the center, or we call the distance from the points to the center, that's this right here. You probably remember that from maybe 6th grade or something like that. That is the radius. So let's start off today by just running through a little bit of vocab to make sure we have understanding of what we're talking about. Okay, and so let's start here. Okay, so diameter. What is the diameter? That's this distance all the way across. I think I will do that in red. So distance, need a finer pen. It's the distance across the center of the circle. Okay, the radius, what is that? We just did that a minute ago. That's the distance from circle to center. Circle to center. Circumference. Folks, that's the distance around the outside. Now, previously we've called that the perimeter. So I'm just going to make a note here. It's the circle version of perimeter. Okay, and then these I'm going to label. A sector, think of that like a slice of pizza, so I'm going to label that in here. So that's a sector. This little guy right here is the radius. This thing in red is the diameter. An arc, you could think of that kind of like the crust. So I'm going to label that like this. Okay, so it's not actually the whole slice of pizza, it's just that edge of it. Okay, and that's called an arc. It's curved. So I will color code that for you. The central angle, I think you probably know where that happens. That's the angle right here in the center. And then, what is pi? Okay, so a lot of people say, oh, pi is 3.1415926. Yep, yes, okay, that's a decimal approximation for it, yes. But what does it mean? Where does it come from? I mean, cultures have been looking at this concept of pi for thousands of years, and they've all come really, really close to it, all within what we believe to be about 2 or 3/10 of what we now believe it to be. And what it is, it's the number of times that the diameter would go around the circle. Now that's hard to think about in math language, but let's think about it in terms of a simple example. So imagine that you are here, and this is a pond, and you want to get to the other side of the pond. There are a couple ways you can do that. You could hop in and start swimming. You could walk around the pond. That would work. And maybe you need to drop off mail or something over here. So we're going to drop off some mail, and then we're going to come back over across the pond. So the shortest distance is to go over and back. The longer distance is to go around and back. So how much further is it to go around walking than to swim straight across? So it's pretty hard to visualize just by drawing, but I'm going to do my best here. So what we have is if I take this diameter and I start wrapping it around, it goes about to here. That's about how far it wraps. It runs out of juice. So then we'd need another one. I'm going to use a different color. So then if we did another one, that would go around and about to here. So that's 2 diameters. So the distance from here walking around the circle to there is the same as walking across and back if you went in a straight line, if you could walk on water. Okay, but you're not back home yet, so you got to keep walking. So we're going to go a little more. So here's another diameter, comes to about here. And then we've got that little leftover section down here. So how many diameters did it take? It took 1, 2, 3, and a little bit more. And so that's what the concept of pi is. It's how many times do I need to take the diameter and wrap it around the circle to get all the way around? And the decimal approximation we use is 3.14. So if it takes about 3.14 diameters to go all the way around the circle, let's try to formalize that. So what was it called going all the way around the circle? Okay, we had that a minute ago. That's the circumference. So the circumference, what is that? That is pi diameters. You have to put the diameter on there 3.14-ish times. So that's one way of finding circumference. An alternate way, think about how diameter and radius relate. Like, for example, if the radius is 5, how long is the diameter? Well, it's 5 and 5 again, so it's 10. So that tells us that every time that we have a diameter, that would be twice as big as the radius. So sometimes you'll see this formula written, maybe I would even say most commonly, as 2 times pi times r. And so I think we should probably get that down in your notes right now. That's going to be one of the important things that we're going to use moving forward today. Let's practice using it now to make sure we understand what it is. Okay, so let's do a few examples. A circle has a radius of 5 feet. What's the circumference? Okay, we just said circumference is 2 times pi times r. So that would be 2 times pi times 5. And that would be 2 times 5 is 10. So 10 pi feet. Now, we have to decide if we're going to type pi in the calculator or not. And if you do, you get about 31.4 feet. It really depends on the way the question is written. Now, this is just a math question, so usually we want to leave pi in the answer. Or sometimes it'll say something in the question like, leave your answer in exact form, or leave your answer in terms of pi. So then we don't want to type pi in the calculator. But if they ask us to round to the nearest tenth, or the nearest whole, or round to the nearest anything, then it's time to type pi in. Now let's try question 2. A circle has a circumference of 30. What's the diameter? Okay, let's see. Circle or circumference equals 2 pi r. I'm actually going to show you 2 ways to do this. So circle equals pi times diameter. So these are 2 different methods that we're going to show, and they're both going to run down the page. In both examples, they told us the circumference was 30. Okay, and so then what I'm going to do is I'm going to try to solve these. In this case, I'm going to solve for the radius, so divide by 2 pi on both sides. And on this side, I'm going to divide by pi. We're going to end up finding diameter, which is what they asked for. And so then I'm just going to type in 30 over pi for the right one. And I get 9.5. And then over here, I'm going to type in 30 divided by 2 pi. And I get 4.8, or I'm going to get 4.775. Now, why is it different? Well, this one's radius. Remember, radius is half as big as diameter. So I'm going to multiply that by 2, and then indeed, I do get that the diameter equals 9.5. So both of these methods work just great. Doesn't necessarily make a difference. We already talked about the central angle a little bit. That's the angle that occurs at the center, or this could be another central angle. We'll use 2 there to show that it's different. The way we define arcs is by their central angle. So for example, if we say the measure of arc AC is 30 degrees, we'd say the arc is 30 degrees and the central angle is also 30 degrees. So central angle down here, the denotation of the arc is there. Notice the notation here. We've got a little loop-de-doo guy on top of our AC. What that says, that's the arc that starts at A and goes to C. Semicircle, you probably already knew that was half a circle, but these next 2 down here might be new to you, okay? Major and minor. Major means big, minor means small. So a major arc means an arc that's more than half the circle. A minor arc is an arc that's less than half the circle. So let's write down an example of each of those. So we have already a minor arc right here, AC. I want to try a different one. I want a different arc that is less than half the circle. So if I go from C to B, that would be an example of a minor arc. Now we need a major arc. I'm going to go again from A to C, but if I went around the long way, took the long route, maybe the scenic route, then that would be more than half the circle. In fact, that would be most of it. So this is how I like to, like cut my cake on my birthday. I'll cut out the little slice right here, and then I pick up the rest of the cake and take it and leave that little slice for everyone else. So if I'm going to do that, though, a lot of people will say, oh, that's arc AC, because it starts at A and it goes to C. But the problem is, with this notation, what we're claiming is we want the shortest possible distance. So what you have to do is not only say, yeah, I'm going from A to C, but you have to say which direction you're going to get from A to C. So we're going to go from A, we're going to go through point B, and then we're going to hit C. So now we have here the arc that starts at A, goes through B, and ends at C. That matches what we have on the picture. And we should probably put a semicircle on there as well. So to me, a semicircle looks like it probably goes from A to B like this. The only issue is, again, if I say semicircle, A to B this way is a semicircle, but if I go underneath, that's also a semicircle. So which way am I going to go? Well, I've chosen to go up on this one, so I need to write A, C, B, because I need 3 points if I'm going to do half a circle or more. Okay, so that's that. Now let's do this numerically. We're actually going to find some angle measures. Okay, the first thing that we want to remember is all this stuff is happening inside a circle, meaning all the total angles are going to have to add up to 360 degrees. Oftentimes, not always, but often that can make this a little bit easier. So let's run down the list here with that in mind, and let's try to fill in these numbers. So from D to X, okay, they gave that to us. That's 56. That one was easy. Y to D, they gave that one to us. That was easy, 40 degrees. X, W. So that's over here, X, W. Okay, interesting. One thing I want you to notice, see right there, letter C, they did not choose that letter on accident. That's on purpose. That's to tell you that's the center. And if that's the center, that means this guy that I'm tracing right here, that's a diameter. Now, if that's one straight line, then you have a linear set right here. So if you've got 40, 56, and something, those three things, if that's one straight line, that has to add up to 180 degrees. So all I'm going to do is take in, and I've got my calculator right here, 180 minus 40 minus 56, and I get 84 right here when I do that. So XW is 84. DMX, let's see, D to M to X. Okay, that's most of the circle. So what I think is the easiest way to do that, you can think about what's included in that arc, but I think what's even easier is to think about what's not included. And what I see that's not included is that. So we know the circle's going to sum up to 360. The 56 is not being included, so what I'm going to do is 360 minus 56, and that should be 304. Okay, and then MW. MW is over here. Oh, I've erased my 4. MW is over here, and this is a little bit tricky for some people, although look again, we have one line right here, which means we have a linear pair, so those two angles are going to have to add up to 180, and so that means this is 96. Now, this last one down here, I've left that there. Oh, degrees, degrees, degrees. I've left that blank because a lot of times in class I like to have people actually make up their own arc and try to figure out what it is. So since this is a video, I can't ask you what you want to choose. I'm just going to make one up, and I want to do arc DM right now. And so this might be a really good chance to pause the video and try this one on your own. Okay. Thing that I noticed from D to M, I know I've got my 40, but I need to figure out what's there in order to get DM. But again, I know this is 96, and actually, I know that this angle and this angle are vertical angles, so this is actually, let's see if I can do this. That's actually 84 right there. So 84 and 40 added together is 124 degrees, and so now that one is done. One of the coolest applications of circles that I like is pie charts. And so we have one here where we have a Costco survey where they wanted to see the membership, what percentage of their membership fell into each of these age ranges. So 65 and older, how many of them are 25? Looks like not a lot of people with Costco memberships are under 25. Looks like 45 to 64. Looks like a lot of moms and dads and grandmas and grandpas probably. So that probably makes sense. So here's the question we have to ask. To the nearest whole number, what is the central angle for each age range? Okay, they want us to find angles. So it's very similar to the previous question where we had to find the number of degrees in these angles. Except we have a little bit different information. We have percentages. And so one thing we need to think about for a minute is what the word percent means, because this is really easy to forget, and I want to reteach you that in case you forgot. Percent. I want you to think of it as two words, percent. Per meaning like out of, and cent, how many cents in a dollar? 100. So 25%, what that means is 25 out of 100, which is 0.25. That's functionally what it means. Now, we know the circle has 360 degrees in it. And so we have 25% of those. So what I'm going to do, to type it in a calculator, you need 0.25, and then I'm going to multiply by 360 degrees, and I get 90 degrees when I do that. Now, folks, take a look. Does that look like a 90-degree angle to you? It should, and the math verifies that. So I'm going to write my answers right over here. That one's 90 degrees. Now let's go down to the one that has an 8, and I'm just doing them in order here. So I've got 8%. Now how are we going to write 8%? Remember, 8% means 8 out of 100, and that's 0.08. So I'm going to come right down here. That's 0.08 of 360, and that one I probably need a calculator for. And that is 28.8. We're going to round that to the nearest whole. And so my answer over here is going to be 29 degrees. Okay, now we've seen two examples. This would be a great chance for you to pause the video and try the rest on your own, or leave it running and try to beat me. See if you can do these faster than I'm going to do them. For the next one, I'm going to do 0.27 times 360. And I get 97.2 when I do that. And so I'm going to write 97 degrees as my answer there. And that makes sense. 25% gave us 90. 27% is a little bit bigger angle. And then we have one more. So 40 degrees, or 40%, excuse me, is 0.4 times 360. And calculator time. And I get 144 degrees. Okay. And so I've got all my answers over here. And we're all done. A common test style question that we'll run into is we're going to be asked to find an arc length. Circumference isn't really a high school level question. It's pretty simple. But having to think a little bit more deeply about finding part of the circumference, because I hope you can see the whole circle all the way around, we're talking circumference. The highlighted arc, we're not talking about the whole circle. So what we're going to start out with, the way that helps me, is if I'm finding the arc length is part of the circumference. Okay, and if it's part of the circumference, I'm going to break that down into mathematics. I know the circumference is 2 times pi times the radius, and then I have to figure out what I mean by part of. So keep in mind, a circle has 360 degrees in total. This arc does not have 360 degrees, because look at what's missing. This little slice of pizza got cut out here. It's missing 90. So this angle on the other side is 270. Now folks, if that went too fast, to verify it, try this. 270 plus, the little box says that's the right angle, that's 90. 270 plus 90 does in fact make 360 degrees, so that's how we can feel comfortable with that being 270. So when I say part of the circumference, I mean 270 degrees out of 360 degrees. And so to rewrite that, 270 out of 360 times 2 times pi times the radius, which is given right here, which is 18. Now, this is usually the part of class where a student says, hey, Mr. Boyden, don't you see that we have exactly 3/4 of the circle, and so we could have just as easily written 3/4 right there? Yeah, absolutely, we could have. Folks, that would have absolutely worked. The reason why I've chosen not to do that is because, yeah, that's 3/4 of the circle. But what if you had an example where you couldn't tell how much of the circle it was? Like if this were 272 degrees, it would be very hard to write a simplified fraction. The other thing you could notice, this 270 out of 360, that absolutely simplifies to 3/4. So if you're thinking that way, you're right. And if you wanted to take that shortcut, you could. But what I'm trying to teach you in these videos is I'm trying to teach you techniques that will work every single time, no matter what. I'm not trying to teach you cheap shortcuts that will work sometimes, because we can't afford to only be right sometimes. We're going to do our best at least to try to be right every time. So now that we get to here, we can type this in. So 270 over 360 times 2 times 18. Uh-oh, I got to think for a minute. Am I going to type pi in the calculator? This says leave answer in terms of pi. So no, I'm not. I'm only going to type in the whole numbers. And so then what I get is I get 27 pi meters as the length of that arc. Let's do a few more, see if we can get a little better at these. Okay, now this is going to be our second one, very similar to the one we just did. So you could probably pause the video and try this one at this point. In fact, try to at least get this set up without help. Okay, so here I go otherwise. So what we're going to have on this one, 30 degrees is important, but it's not our arc. We're talking about the red arc, and that's going around the long way. So that's going to be 360 minus 30, and that is 330 for that arc. Okay, so I'm going to get 330 out of 360 times 2 times pi times, wait a minute, 36. That looks like it's in the middle, so that's going all the way across. The radius is not 36. The diameter is 36. So I'm going to put in 18 right here, because if I had 18 there, and I had 18 for the radius on each of these, then 18 plus 18 would give me 36. So now, calculator time. So 330 over 360 times 2 times 18. I'm not typing in the pi, and when I do this, I get 33 pi inches. Done. One more. And here it is. Folks, try it on your own. Determine the length of arc CDE. CDE. All right, y'all, you know the drill. Pause the video and try it, and then hit play, see how you did. Here I go. What I'm going to have here is 320 over 360 times 2 times pi times 9. Calculator time. 320 over 360 times 2 times 9, and I get 16 pi centimeters. All right, y'all, that's going to do it for today. Hope you enjoyed the video, and we'll see y'all next time.